When a large language model finishes its training phase, its internal structure becomes fixed. It is a frozen set of mathematical weights. It receives no gradient updates, acting as a static predictor that guesses the next word based on a snapshot of data from the past. Yet these static engines are the core of highly dynamic systems that research, code, and act autonomously in the real world. This capability doesn't stem from a change in the weights. It happens at the inference layer, the architectural space where the model is actually queried. AI capability now scales through engineered context manipulation at runtime, moving beyond the traditional reliance on increasing training time parameters. Transforming a closed predictor into a functional problem-solving system requires building a specific architectural wrapper around those frozen weights. This diagram breaks down the baseline mechanism, in-context learning.
We have our frozen model block, and attached to it is the context window. When we place text into this window, whether it's a simple zero-shot instruction or a few-shot prompt containing example pairs, the model conditions its output entirely within the forward pass. Standard next token prediction has a critical weakness. If we feed a complex, multi-step math problem into the context window, the model is forced to produce a single, immediate output token. Without room to process the logic, it effectively guesses. Chain of thought prompting provides a mechanical solution to this single pass limitation. By instructing the model to think step by step, we change the way it uses the context. Because the model is auto-regressive, every intermediate token it generates loops directly back into the context window. By writing out its intermediate steps, the model creates a computational scratchpad, conditioning its final answer on the work it just completed. Generating more intermediate steps requires the model to spend more computation before committing to an answer. This introduces a new scaling access, test time compute. This chart highlights the direct correlation between compute and reliability. On complex logic tasks, a standard model using 50 tokens might hit 40% accuracy. A reasoning model using 2,000 tokens of step-by-step work costs 40 times more in tokens and latency, but accuracy rises to 85%. Reasoning is now an economic variable. Engineers can mathematically justify the cost of inference compute for high-stakes tasks where accuracy is mandatory. Even with deep reasoning, frozen weights retain two immutable flaws: a hard knowledge cutoff date and a statistical tendency to hallucinate plausible-sounding falsehoods. Retrieval-augmented generation, or RAG, is the architectural pipeline designed to force the model to reason over fresh, verifiable text. RAG operates in two phases. In the retrieval phase, an incoming user query is congery into a mathematical representation called a vector embedding. That query embedding is then mapped against an indexed database using a cosine similarity search, which extracts the most mathematically relevant document chunks. In the generation phase, those retrieved chunks are injected directly into the model's context window alongside the original prompt. By supplying the evidence at query time, RAG turns the LLM into a grounded reasoning engine operating on provided facts. At this point, the model can reason and read, but it remains isolated. It cannot execute exact arithmetic, alter a codebase, or natively ping real-time APIs. We cross this boundary using tool use, also known as function calling. When the model identifies a task it cannot perform alone, it is configured to pause natural language output and emit a structured request, like a JSON string, specifying a function name and arguments. The surrounding system parses that structured format, executes the external tool, and pipes the result back into the context window so the model can continue. The engineering power here relies on the model's learned behavior. It must decide when a tool is required, which one to use, and what arguments to pass to it. Tool use transforms the LLM from a closed, isolated oracle into an active orchestrator of diverse external capabilities. A single forward pass, even one equipped with external tools, eventually terminates. Multi-step, open-ended tasks require a different approach. We achieve this by wrapping the entire architecture in a continuous react, or reason plus act, loop. When given an objective, the agent cycles through distinct stages. It plans the next step, acts by calling a tool, observes the return data, and then updates its plan based on that new information. Because this process repeats until the goal is met, the system can autonomously debug scripts and correct its own logic errors across dozens of iterations. This continuous inference time feedback loop is what allows the model's pre-trained logic to manifest as sustained, goal-oriented autonomy. We can scale this further by building multi-agent systems. Here, specialized roles and cross-critique functions are distributed across multiple instances of our agent loop, all managed by a central orchestrator. Decomposing a complex goal and delegating the subtasks to specialized agents can outperform a single prompt attempting the entire task alone. However, this approach carries high engineering costs. Every recursive call and inter-agent communication increases token expenditure and system latency. Orchestration also introduces failure modes. You risk compounding errors as bad data propagates between agents, or getting stuck in infinite loops. For practical deployment, a single, highly capable model equipped with well-tuned tools is often superior to a complex web of multiple agents. This matrix shows the complete system. Prompting directs the task. Chain of thought deepens the compute. RAG grounds the knowledge. Tools extend the action. And the recursive loop enables autonomy. Development has shifted from the brute force scaling of training data to the design and optimization of these robust inference time systems.